Early stargazers, especially those in Egypt and ancient Babylon of semi-desert countries where skies are rarely clouded, were fascinated by the star-studded sky arc overhead and by the daily motion of the sun, which seemed supernatural, beyond understanding. Imagine you were one of the early Babylonian sky watchers living on a plan. It is all too natural that you think the earth is flat, and your view is limited by the horizon. Observing day after day, you note that the sun always rises up from roughly the same direction, which you name east. It sets in the opposite direction, which you name west. As observing from most parts of the northern hemisphere, the sun moves across the sky in a long arc, the furthest from the horizon, which is halfway between rising and setting, a direction facing the sun you call south. Eventually, the direction opposite south will be north. When the sun is near the horizon, shortly after sunrise or before sunset, a vertical column or pole casts a long shadow at the highest position in the sky. When it is in the south, the shadow is at its shortest. The time when this happens is halfway between sunrise and sunset, which we call noon. When you watch the sunrise and set day after day, you realize that the point where sun rises and sets are not always the same, but shift week after week. On the other hand, the direction of south where the sun reaches the highest above the horizon does not change, and neither does that of north, where there is the shortest shadow of the day. Since the directions of north and south are fixed, so the best way to choose the east and west, those directions which are perpendicular to north-south directions. Only twice in each year, the sun will rise and set exactly in those directions. In other days, the positions of sunrise and sunset are either to the left or right of the true east and west respectively. To ancient people, especially those stargazers, all celestial body, including the sun, the moon, the stars, seem to be distributed randomly on the surface of a big sphere called celestial sphere. To ancient observers, it seemed as if Earth was the center of this giant star-studded sphere. If you watch stars throughout the night, you see that most of them also rise to the east and set west of you. The entire celestial sphere seemed to rotate slowly like a spinning lamp. It takes 24 hours to complete one rotation. As observing on Earth, since half of the celestial sphere is always hidden under the horizon, the Earth rotation constantly brings out new stars on the eastern horizon, while others to disappear beneath the western horizon. Of course, we now understand that it is not the universe that rotates around the Earth from east to west, but our Earth rotating from west to east. Celestial sphere is a useful model to help us to understand the movement of stars as seen from the Earth. The celestial sphere is an imaginary sphere whose center coincides with that of the Earth. All celestial bodies are thought to be on this imaginary sphere. The model of celestial sphere can effectively describe the sky we see at night. However, it is certainly not a correct model to describe the universe. For instance, stars are not of equal distance from the Earth. The Earth rotates steadily from west to east. More precisely, the Earth rotates anti-clockwise when observing on the North Pole facing the Earth's center. That is why we see the celestial sphere and celestial bodies on it appears to rotate steadily from east to west when observing on the Earth. The points where the rotational axis of the Earth intersects the celestial sphere are called the North Celestial Pole and South Celestial Pole. Since the rotational axis of Earth coincide with the rotational axis of the celestial sphere, celestial body appears to rotate steadily around the celestial poles. The celestial equator is the projection of Earth equator onto the celestial sphere, dividing the celestial sphere into two equal halves. In the celestial sphere model, the Earth is assumed to be at rest while the celestial sphere, together with all the celestial bodies attached to its inner surface, rotate around Earth once every day. This motion is called the daily motion of the celestial sphere. While observing on the Earth, you can only see half of the celestial sphere, while the other half is obscured by the Earth. The stars appear to rotate steadily around the celestial pole, as the angle between the celestial pole and the horizon is not the same at the different latitude, so the movements of the stars depend on our latitude on the Earth. If we were observing in the northern hemisphere, stars close to the northern celestial pole never fall below the horizon. These stars are called circumpolar stars. Similarly, those stars close to South Celestial Pole will never rise above the horizon, and they cannot be seen in the northern hemisphere. Stars close to the celestial equator rise and set every day. When observing on Earth, the position of celestial poles and celestial equator depend on the latitude of the observer. Imagine that we observe the sky at the place of latitude of 22 degrees in the northern hemisphere. Then the angle between northern celestial pole and the northern horizon is 22 degrees. Since the celestial pole is perpendicular to the celestial equator, the angle between celestial equator and the horizon is 68 degrees. Looking northward from this point, you see stars rotating around north celestial pole in an anti-clockwise direction. Some of them are circumpolar stars. Stars in the east rise at an angle to the horizon and set in the west. Looking south, we can see stars rotate in a clockwise direction around the south celestial pole and eventually invisible below the southern horizon. Imagine we observe the sky at the Earth equator. The latitude at the equator is 0 degrees, hence the north celestial pole is in north direction at the horizon. All stars are seen moving in semicircles around the north and south axis. Stars rise up in the eastern half of the horizon, moving across the sky and set straight down in the western half of the horizon. Now imagine that we are at the North Pole of latitude 90 degrees and the North Celestial Pole is directly above our head and the celestial equator coincides with the horizon. Because of the daily motion of celestial sphere, stars are seen to rotate around the northern celestial pole in concentric circles. They are always there and never rise and set. At the North Pole, all stars above the horizon are circumpolar stars. The Earth orbits around the Sun in a year. As observed from the Earth, the Sun appears to move across the background of motionless stars fixed on celestial sphere. As seen from the Earth, the Sun moves around the celestial sphere once every year. The apparent motion of the Sun is called yearly motion. The trajectory of the Sun on the celestial sphere is called elliptic. If the rotational axis of the Earth were not tilted and is perpendicular to its orbital plane, the elliptic and the celestial equator would coincide. In reality, the rotational axis is tilted at an angle of 23.5 degrees. This tilt makes the ecliptic to incline at an angle of 23.5 degrees to celestial equator. The ecliptic intersects the celestial equator at 2 points, called the vernal equinox and autumnal equinox. The sun crosses the vernal equinox on March 20 or 21st each year. After that, the sun goes northward and reaches the furthest north position called summer solstice on June 21st or 22nd. Then the sun heads southward and crosses the celestial equator at a point called an autumnal equinox on September 22nd or 23rd. After that, the sun continues to go southward and reaches the furthest south point on December 21st or 22nd, and this point is called winter solstice. Finally, the sun will go northward, returns to the vernal equinox. The cycle is then starts all over again. The rotational axis of the Earth is tilted at 23.5 degrees from the perpendicular to its orbit. As the Earth revolves around the Sun, the direction of the axis remained almost unchanged. This is the cause of seasonal changes. As observing from the Earth, the daily path of the Sun is not exactly the same every day. We can understand the seasonal changes better with the help of the celestial model. On the day of summer solstice, the sun is still north of the celestial equator. When observing in the northern hemisphere, the sun rises and sets on the farthest north position. The path of the sun across the sky is the longest, and so is the day. On that day, the sun is relatively high in the sky. The daytime is the longest and receives the maximum amount of sunlight. The day of summer solstice is regarded as the beginning of summer in the northern hemisphere. On the day of winter solstice, the sun is due south of celestial equator. When observing from the northern hemisphere, sunrise and sunset are as farthest south position. As a result, the sun has its shortest path across the sky for the year. The day is at its shortest and night is at its longest. This is also the day of the Earth receives the minimum amount of sunlight. The day of winter solstice is regarded as the beginning of winter in the northern hemisphere. On both the day of vernal equinox and autumnal equinox, the sun rises in the east and moves across the celestial equator and sets in the west. The daytime and nighttime are equal in length in both hemispheres. The days of the vernal equinox and an autumnal equinox mark the beginning of spring and autumn in the northern hemisphere. The southern and northern hemisphere received equal amount of sunlight. There is no longer daytime in summer than in winter. However, this is not the only reason why summer is hot and winter is cold. In the northern hemisphere, the path of the sun in daytime is a curve across the southern sky. At noon, the sun reaches the highest position in the sky. As the path of the sun across the sky in summer is longer than that in the winter, the rays of summer sun high in the sky arrive at the steep angle and the land is heated much more than those of the winter sun. When the sun is near the horizon, not only is the shadow, which is cast stretched to greater length, it also spread out a greater distance on the ground. Hence the heat given to that area is also reduced. The sun at noon in winter is at a lower position in the sky, and its heat is less pronounced. The summer sun at noon is almost overhead, heating the ground much more effectively. The length of a day together with the angle of sunlight help to explain why it is hot in summer and cold in winter.